Hi, I'm Tristan Gaskins, and my video is on gravitational waves and the other phenomena of Einstein's theory of relativity, based on the lecture based on gravitational waves, thanks to the discovery, which was held by students and professors here at Georgia Tech. So to start off, let's give a little basis of gravitational waves and general relativity. General relativity stipulates that interacting masses, no matter how large, while producing a direct effect on each other, also produce an effect on the space-time around them, by losing energy emitted through gravitational waves. This provides an outing through which such masses can lose not just kinetic energy, but also angular and linear momentum, or at least which allows for the creation of objects otherwise undefinable within the universe, such as supermassive black holes and naked pulsars. Although everything technically produces these waves, the creation of a deformation from objects even the size of the Earth and our Sun are magnitudes smaller than what we're able to detect. Therefore, we search for other interactions through which to find evidence of these waves, which were hypothesized nearly 100 years ago. Such interactions include interstellar bodies on an in-spiral towards each other. Before we get into in-spiral creation of detectable waves, let's take a look at the other major phenomena from Einstein's theory of relativity: black holes. Well, we've all come to know the basics of black holes: the inability of anything to escape, the supercondensed center with near infinite gravitational pull, and a whole variety of myths and statements deserving of even the Greek gods. The basic principles controlling black holes are their event horizons, the point beyond which nothing can escape said black hole, their inexplicably resilient nature, and their creation from a collapsing mass of at least 2 to 3 times the size of the Sun. Although they generally serve as a catalyst for a variety of events throughout science fiction media, their true nature is actually just as complex as is portrayed, but maybe not as miraculous. For example, a black hole generally looks less like this, and more like this. What we know about black holes is extremely limited, though, because we can't view anything past the event horizon, a distinct distance away from the center from which nothing can escape. What we do know is how they affect other celestial bodies, by serving as centers to galaxies and by swallowing pretty much everything they can get their hands on. Now, let's travel a little outside our lecture to look at Hawking radiation, which essentially states that black holes are slowly losing mass and energy and ever so slowly shrinking. These principles are only applicable to spinning black holes, though, because the angular momentum they possess must be going somewhere. By slowly throwing out particles, they gain speed and lose mass, which inevitably speeds up the process until they just suddenly disappear. Now back to gravitational waves, which share a striking resemblance to Hawking radiation. Both are a means for which celestial bodies can lose the necessary energy to interact with the waves that we've observed. Much in the way that black holes have Hawking radiation, gravitational waves are generally observed due to. The process involves the release of energy from the system, and its steps are vaguely similar to giving off energy, get smaller in orbit, and speed up a little bit. Rinse, wash, repeat till eventually the two objects merge generally into either a supernova or a larger black hole. Before we talk about the actual implications of this discovery, we should look at what's been brought up in popular debate. The two main possibilities by these detections are that of faster-than-light travel through the use of a modified Alcubierre drive, which would operate much like a surfboard on the ocean, and the potential forms of communication, which even prompted the DIA to launch an investigation. Sadly, neither of these two possibilities could happen in the near future, because both require a stable means of creating the waves, which means the containment of two black holes. Although the gravitational waves might not affect us in this way, they still have implications to humanity as a whole. This part might be a bit of my own conjecture, but the two processes are like two sides of the same coin. Inspiraling gravitational waves are going towards the creation of a black hole or larger celestial body. And black holes are going through a similar process, but losing that mass and energy to what they were created from. So it's sort of like a birthing and rebirthing process that may go on forever, even if everything will eventually lead to a black hole. Speaking of the future, there are very long-term effects of gravitational waves on us. Firstly, eventually our Earth will hit the Sun, but don't worry, it's about 1.6 times the age of the universe as we know it away. But the discovery helps us better understand the universe and interpret the interactions we've been observing around us. To me, this seems like a cycle of rebirth that will eventually affect us once we've left this planet and we go searching for a new permanent home, which ironically might currently be at the center of a black hole. But I guess we might never know in our lifetimes. But if we do, we'll be there together.